Welcome to our video lecture on quantum mechanics. What even is quantum mechanics? So quantum mechanics is thinking about how atoms and subatomic particles interact. Subatomic particles, electrons, protons, and neutrons. We're going to do a lot of the math of this today, so definitely pause the video. Make sure that you've got a calculator nearby. The formula that we're going to use are on your reference pages, so I also would grab a periodic table. Our objectives for today, we're going to review the Bohr model of atoms because quantum mechanics is a total bore. Get it? It's good. We're going to describe emission spectra. We're going to define wavelength and frequency. We're going to talk about the relationships amongst wavelength, frequency, and energy. This is a lot of physics in chemistry, my friends. Then we're going to do the math of calculating wavelength, frequency, and energy. So how are Bohr and quantum mechanics related? So our Bohr model, here we know that we've got nucleus and we've got these energy levels where we find electrons, and the electrons in those energy levels are associated with different quantities of energy. What's kind of cool, we can actually get those electrons to absorb some extra energy, and they have to jump to a higher energy level because they have higher energy. But this isn't stable, and so what they'll do is they'll release that energy, and then go back down to that lower energy level called the ground state. So when they have more energy excited, when they go back down to normal lower energy, it's ground state. So sometimes that energy that is released when those electrons go back down to ground state is in the form of light. And so here's a little bits of physics about light. Visible light is part of the electromagnetic spectrum, so are X-rays and microwaves and radio waves. Newton thought that light was made of particles, and then scientists in the early 1900s were like, no, Newton, you were wrong, it's waves. Then along comes Einstein and he says, maybe you're all right. So Einstein proposed that light is comprised of these packets or quanta of energy. These packets of energy are called photons. So it's energy, but it acts like a particle and it travels in waves. So it's like a particle, but it travels in waves. And so we're going to talk about waves a lot today. So back to this idea of emission spectra. When those atoms are hit with energy, they jump to a higher energy level. That's called excited state. Because those electrons have more energy, they have to be in that higher energy level. Those electrons have higher energies. But that's not a stable configuration. So the electrons will drop back down to a lower energy level. And that energy can be, I shouldn't say is, that energy can be released as light. We notice with our eyeballs when it is. It's kind of exciting. The energy can also be released as infrared or UV, but we're going to focus on the energy that we can see as visible light. That light comes in lots of different colors, which is kind of cool. We'll see all the pretty colors in lab. So basically what happens is this. We have our electrons, and those electrons jump to a higher energy level. If they jump back down, or rather fall back down to energy level number 2, we're going to see that visible light. If it's just a short jump, like from 3 to 2, that's just a little bit of energy, and so we're going to have visible light that's low energy, and that's red. Red is low energy. If we have medium colors like greens and blue-greens, from 4 to 2, we'll have those middle colors, greens and blues. If we have big energy, like 5 or 6, energy level number 5 or 6, back down to energy level number 2, we'll see the big energy colors, blues and purples. So if you are one of my artists, you might be noticing that this is Roy G. Biv, right? Low energy light is in the reds and oranges. High energy light is in the violets and purples. So once again, what we're going to do is knock these electrons around by getting them to add some extra energy. They'll jump to a higher energy level. If they have a little bit of a fall back down to a lower energy, they're going to release little bits of energy, and we can see that in light in red. If they jumped up crazy high because they absorbed lots of energy, and they fall all the way back down to 2, then we're going to see the release of that big energy in the forms of purples. So these are emission spectra, and what's kind of cool is that different elements have different emission spectra because different elements have different arrangements or configurations of electrons. So because hydrogen has 1 electron that can jump around and sodium has 11 electrons that can jump around, they're going to jump in different ways, and then they will have these rainbows of colors of their electrons jumping around different. Astronomers can actually use this, look at light coming from space, and they can determine if stars have neon or mercury or helium in them based on their spectra, because we can match the spectra coming from space to the spectra that we have here on Earth. And these different elements, again, have different spectra because they have different configurations of electrons. Because each element has a unique electron configuration, they will have unique emission spectra. So we've been talking a lot about light, and I mentioned that we're going to do some physics. Here's physics. So frequency and wavelength of waves. You probably did this in middle school, so it should be a quick, easy review. So the wavelength is literally the length of a wave, right? So sometimes we like to go from crest to crest. You could also go from trough to trough. But the wavelength is just that distance of the repeating wave, right? We can have longer wavelengths. We can have middle wavelengths. We can have super short wavelengths. Wavelength is related to frequency. So frequency is how many waves are passing a given point in a second. So in this graphic, we've picked this to be our space, our given space. And for 1 second, we watched these waves go by. And for this first wave, we only had 1 wave pass. And so we would measure frequency in hertz. So you have 1 wave per second. That's 1 hertz. It's hertz like this, H-E-R-T-Z, but we abbreviate H-Z. This wavelength is a little shorter, which means that I can get more waves to pass. Here's 1.5 hertz. And this guy that has a super short wavelength, I can squeeze in a bunch of waves in here. It will have a frequency of 3 hertz. So notice that big wavelength, lower frequency. Short wavelength, bigger frequency. So they kind of go up and down with each other. It's an inverse relationship. So we have these formulae on our periodic tables to help us calculate frequency, wavelength, and energy. So all these guys in atomic structure, the speed of light is equal to frequency and times wavelength. C equals frequency wavelength. Energy can be equal to Planck's constant times frequency, or we can do Planck's constant times the speed of light divided by wavelength. Both of these are here. We're looking at the energy in a photon, those photons, those quanta of energy. So you may have noticed Planck's constant speed of light. You're like, I don't know what those are equal to. That's okay. We have our list of constants and conversions. Planck's constant is right under Avogadro's number. Planck's constant is equal to 6.63 times 10 to the negative 34. That's really, really, really small. Joule time second. Joule is our unit of energy in the metric system. So Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Speed of light is here, 3.00 times 10 to the 8 meters per second. Good? All right. So here's a problem that you might see where you would have to use some of these formulae. So hydrogen has a red emission lines. Remember, we looked at those rainbows in the red, and there was that red. So that red emission line has a wavelength of 656.3 nanometers, which is equal to 6.563 times 10 to the minus 7 meters. We need to calculate the frequency and the energy. Let's review our formulae. So we're going to start with the frequency. So calculate frequency first, and I'm scanning my formulae here. I have wavelength, I need frequency. Which formulae has frequency and wavelength? This one has frequency and wavelength. So this is the formula that we're going to use. Speed of light equals frequency times wavelength. Let's go figure out what speed of light is equal. So let's go ahead and actually do this calculation now. We have frequency first. We're going to use that formula. Speed of light equals frequency times wavelength. Speed of light equals frequency times wavelength. That's the Greek letter lambda. We're going to use it for wavelength. Speed of light. Speed of light is here. I'm going to plug this in for C. 3.00 times 10 to the 8th meters per second. I'm going to set that equal to frequency. Frequency is that I don't know yet. Frequency times wavelength. Wavelength is here. Since my speed of light is in meters, I need my wavelength to also be in meters. So I'm going to plug in this version, not this version. So in meters, 6.563 times 10 to the minus 7 meters. To solve for frequency, we're going to divide both sides by the wavelength. 6.563 times 10 to the minus 7 meters. That allows us to cancel that out. On the right side, we just have frequency left. On the left side, we're going to divide by that same wavelength, 6.563 times 10 to the minus 7 meters. Thank goodness I have my calculator because this is some messy math. All right, so 3 times 10 to the 8th power divided by 6.563 times 10 to the negative 7 power is going to give us a frequency of 4.57108029 E14. What does that even mean, and how many sig figs should I keep? All right, so sig figs, I have 3, I have 4. We get to keep 3 because 3 is fewer. So 1, 2, 3, that 1 doesn't do anything to that 7. 4.57 E14 times 10 to the 14th. Let's talk about what our unit label is going to be. So my meters, top and bottom, canceled out. I'm left with divided by seconds. We're talking about waves. Waves per second means hertz. So my unit label is going to be hertz. 4.57 times 10 to the 14th hertz is our frequency. Good. Now we can finish the problem and calculate energy. Frequency done. Energy next. So energy equals, we have 2 options for this formula. We can do Planck's constant times the frequency, or we can do Planck's constant times the speed of light divided by wavelength. Since we're given wavelength, we're going to use this guy that has the wavelength and the energy. And I'm going to get rid of those scribbles so we can actually see the formulae. All right, so we're going to use this one. Energy equals Planck's constant times the speed of light divided by wavelength. Both of these guys are constants. So we're going to start with lots of constants. Planck's constant is here. 6.63 times 10 to the negative 34 joule seconds. We're going to multiply that by the speed of light, which is here. 3.00 times 10 to the 8th meters per second. Good. We're going to divide that by the wavelength. The wavelength is given to us here. 6.563 times 10 to the minus 7 meters. Thank goodness, once again, we have our handy-dandy calculator ready. There's nothing to solve for. I don't have to do any crazy algebra. It's really just plug and chug. This guy, Planck's constant, times this guy, speed of light, divided by this guy, wavelength. Let's do it. All right, so calculator turned on. 6.63 times 10 to the negative 34 times 3.00 times 10 to the 8th divided by 6.563 times 10 to the negative 7 is going to give us a grand total of energy equals 3.03066, lots of digits, times 10 to the negative 19. Sig fig check. I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. I get to keep 3. 1, 2, 3. That 0 doesn't do anything. So it's going to be 3.03 times 10 to the negative 19. Let's look at our unit labels. Seconds and seconds cancels out. Meters and meters cancels out. We're left with joules, which is good because joules is our unit of energy. We did it. Let's do one more problem. All right, so one type of sunburn occurs on exposure to UV light that has a frequency. We have a frequency of 9.23 times 10 to the 14th hertz. We're going to calculate the wavelength and the energy of that photon of UV light. Good. All right, so we're going to start with frequency and wavelength. We have frequency and wavelength. The formula that puts those two together is here, frequency and wavelength. Speed of light, c, equals frequency times wavelength. Speed of light is here, 3 times 10 to the 8th meters per second, 3.00 times 10 to the 8th meters per second. We're going to set that equal to the frequency, which is given to us in the problem, 9.23 times 10 to the 14th hertz. We're going to multiply that by the wavelength. The wavelength is what we don't know, so we're going to use that Greek letter lambda. To solve for lambda, the wavelength, 9.23 times 10 to the 14th is going to get divided on both sides. Divide on both sides. Oops, that's a 9.23 times 10 to the 14th hertz. Handy dandy calculator time. 3 times 10 to the 8th divided by 9.23 times 10 to the 14th power is going to give us 3.250270, lots of digits, E-7. Let's check our sig figs. I have 3, I get to keep 3, 1, 2, 3, that 0 doesn't do anything to that 5. So the wavelength is going to be 3.25 times 10 to the minus 7. So quirky thing about the unit labels, remember that hertz kind of cancels out seconds in the denominator. So hertz and seconds cancels out. We're left with meters, which makes sense because I'm looking for the length of the wave, and those comes in meters. Here's our wavelength, 3.25 times 10 to the minus 7 meters. Now we need to do energy. We can squeeze it in, I promise. So energy is going to be equal to either Planck's constant times frequency or Planck's constant times the speed of light divided by the wavelength. Since I have the frequency in the problem, I get to use the easier formula. Yay! So energy is just going to be Planck's constant times the frequency. Energy is going to be Planck's constant times the frequency. Planck's constant is given to us here, 6.63 times 10 to the negative 34 joule seconds. We're going to multiply that by the frequency, which is given to us in the problem, 9.23 times 10 to the 14th hertz. We just need to multiply. Handy dandy calculator time, 6.63 times 10 to the negative 34. Multiply that by 9.23 times 10 to the 14th hertz. And that gives us a grand total of 6.11949. Let's check our sig figs. I get to keep 3, 1, 2, 3. That 9 is going to make that 1 a 2. 6.12. Let's look at our exponent. Times 10 to the negative 19. Let's think about our unit label. So hertz here and seconds here cancel each other out. We're left with joules. That's good because we're trying to find energy, and joules is our unit of energy. My friends, we did it! We know quantum mechanics. We reviewed that Bohr model. We talked about nucleus, energy level, energy level, energy level. The energy levels that are further away from the nucleus have more energy. Emission spectra. We can get electrons to jump to higher energy levels, and then they fall back down to lower energy levels. And when they do that, they emit or release different colors of light, and different elements, because they have different electron configurations, will release different patterns of light. Because light is radiation, we did some physics. We defined wavelength and frequency. We talked about wavelength, frequency, and energy. A long wavelength means a lower frequency. A short wavelength means more waves per second, higher frequency. And then in terms of energy, if you have a long wavelength, it's kind of boring, that's low energy. If you have to scribble really fast and use a bunch of energy to draw your waves, that's high energy. So long wavelength, low frequency, low energy. Short wavelength, so short you can't even see it. High frequency, high energy. And then we did some calculations. Remember that the speed of light is equal to the frequency times the wavelength. Energy is equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by wavelength. Good work, my friends.